Good afternoon, fancy meat computers. How's everybody today? I had a thought as I was watching the slideshow of the pixely images that precedes this lecture. Because one of those is supposed to be, I believe, Rivendell from the Lord of the Rings books / movie. It seems to take after the Peter Jackson movie. And it occurred to me, of Rivendell, it's pretty close to that waterfall, isn't it? Now, if that waterfall is anything like Niagara Falls, which is one of the most powerful waterfalls in the whole world, that waterfall is probably receding at a rate of 1/2 foot a year. And given that the elves are supposed to be immortal, and that is supposed to be one of their old settlements that's 1,000 years old, it wouldn't be with this nice scenic waterfall in the background. It would be, in fact, just a canyon. So Rivendell, properly, geologically, should be just a canyon. That's what I'm saying. Unless it's elf magic, because it might well be elf magic. So, anyway. Hello, Pacific Cod, with your usual exclamation mark. Good. So, announcements. 2 announcements. First, Project 1 has been updated. I've added some additional information to the Project 1 document. Mostly it's hints. But I also restructured the question 1 so that it separates out the type business that you're doing from the single-step semantics from the multi-step semantics. So I think it's a little more clearly organized now, and it takes into account some feedback I had received about the assignment, and so hopefully this is a better assignment. It's more understandable. I think that it is. So if you have an old version that you downloaded, please download the new version. Secondly, we did our usual Monday assignment drop, as well as the Topic 5 lecture slides. So assignment 4 is now released. Pardon me. But of course, the assignment that you have to worry about right now is assignment 3. The active assignment this week is assignment 3. Assignment 4 is the assignment for next week. So nice to have it a week ahead of time, maybe. Topic 5 is on lambda calculus. So, yes. With topic 5, we're going to talk about untyped lambda calculus. But for the time being, we have one section remaining in the operational semantics of untyped expression language to get through before we can make it that far. So let's talk about this. So last time, we went through a fair amount. We talked about normal forms, and we talked about arithmetic operations, and we gave our extended UAE semantics for your predecessor and your successor and is0 functions, in addition to our booleans that we had done earlier. And of course, we introduced a new category of values, which is to say numeric values, because of course some of our rules can only operate on numeric values, or else we lose the property of determinacy. So let's talk about termination. So this is going to be the part where we talk about multi-step semantics, which is part 3 of Project 1, so there you go. Termination. A property of extreme importance when it comes to programs in various programming languages is the property of termination. In our context, evaluation terminates when the term we are evaluating reaches some normal's form. Oh yeah, full screen. There we go. Sorry, I keep forgetting. So, just to recap normal form does not mean necessarily that you've ended up as a value, particularly when we talk about arithmetic operations being thrown in there, because error states are also normal forms. You know, the successor of true is a normal form. It cannot be evaluated any further, but it's also not a value. What normal form means is that it means no further evaluation rule applies to the term. In order for a language like UAE to have any practical utility whatsoever, evaluation must terminate. That is to say, we shouldn't build infinite loops into the very structure of our language. I think we can all agree that that would be a terrible idea. In practical terms, it should be impossible for a finite term to take an infinite amount of time to terminate. I.e., we want to make sure no evaluation rule returns us to a previous state, thus causing an infinite loop in evaluation. So yeah, we have this traditional caveat when it comes to whether or not something should be infinite, right? It's an important caveat to say that finite terms should take a finite amount of time. Because remember, in our language, it is completely and totally possible, theoretically speaking, to construct infinitely terms of infinite size, right? Because it's a recursive definition, they can just go off and march off to infinity. So we're not really concerned that an infinite term should take an infinite amount of time to execute, because we would expect it to. What we're concerned about is a finite term taking an infinite amount of time. So basically, we kind of get this for free out of determinacy, to be honest with you. But this is an important concept in computer language design. Although the halting problem is undecidable for larger languages, UAE is small enough that we can prove termination unequivocally. So, Have you guys heard of the halting problem? If you haven't, I'll talk about it briefly. But, yeah. And I flashed the meme before I got there. All terms will terminate or be terminated. So let's see. Have you guys heard of the halting problem? Yes. Okay, good. Wonderful. That's pretty rare to get 100% on one of these polls. Excellent. It seems you guys covered that pretty thoroughly then. Good. So, multi-step evaluation. Only heard but not understood. Okay. Well, I'll go over it briefly then. And since a few people... Okay, so the halting problem is the question... So, when you're talking about a computer program, not a language, but a program, right? Say you've got a program with while loops in it. You can't determine whether or not that... you cannot determine with certainty whether or not that program will run infinitely until you run it. There are... Basically, there's no proof that you can produce, like, in general for it. So, with halting, like, the reason it's called the halting problem is you're trying to determine whether or not the problem halts, or finishes, or terminates, right? So, for a larger language, one that is Turing-complete, specifically for languages that are Turing-complete, it's undecidable. That is to say, you can prove things about, like, a single particular program. You might be able to prove that your tiny little program halts, but you can't, like, it requires effort. It requires, like, a little bit of intuition and Hoare logic, or something like that. But, you know, whether or not, you know, a class of programs written in that language halt or not, that's, you know, it becomes very, very difficult. UAE is small enough that it doesn't have the problem. If you could make a program that takes programs as inputs and returns true or false, or whether or not halts or not, paradox ensues. Yes, there we go. That's probably, like, yeah, there we go. Yusuf has a much more formal, description of it. You can't write a program that determines whether or not the other programs halt or not. That's the halting problem. So, fortunately, with UAE, UAE is not Turing-complete. You may have noticed that. With UAE, well, in particular, it doesn't hold state, although that doesn't necessarily mean that it's not Turing-complete, because lambda calculus that we'll be dealing with in Topic 5 is Turing-complete, but it does not hold state. It's kind of cool and interesting. We'll get into it. But essentially, in order for something to be Turing equivalent, you need to be able to do branching and you need to be able to do repetition. And UAE does branching, but it doesn't do repetition, so it's not Turing complete. So basically, it can't... The halting problem is decidable because it doesn't have loops, and loops are the problem. But, yeah. So there we go. So, termination... All terms will be terminated, or will terminate or be terminated. Yes, multi-step evaluation. So let's talk about multi-step evaluation, which is arrow star, or eventually evaluates to. I'll probably pronounce this as eventually evaluates to. Let's define the multi-step evaluation relation. Multi-step evaluation is the reflexive, transitive closure of one-step evaluation. Ha! You thought we'd never have to talk about closures ever again, didn't you? You thought that was just in topic 2 and I would never see it again. Hey, nope. That's right. Let's see. There we go. So yeah. Multi-step evaluation is the reflexive, transitive closure of one-step evaluation. That is, it is the smallest relation such that t evaluating to t prime implies that t multi-step evaluates to t prime. For all t in the set of terms, t multi-step evaluates to itself, and t multi-step evaluates to t prime, and t prime multi-step evaluates to t double prime, implies that t multi-step evaluates to t double prime. This last property is critical because it means that if you start with t0, t0, and you end up with tn through a series of applications of single-step evaluation, multi-step evaluation can jump directly from t0 or t0 to tn, or at any point in between with one application of arrow star. So the trick here with multi-step evaluation, it's not necessarily full evaluation, right? It's just multi-step evaluation. We can perform more than one evaluation step. We can represent a series of evaluation steps so long as they have transitivity with one instance of the multi-step evaluation. We're going to find, though, that typically when we talk about this, we are trying to bring our terms into normal form. This is like our shorthand of saying, and then you apply as many evaluation steps as is necessary to achieve normal form. Is t0 to multi-steps evaluates to t0 also valid? Yes, because it is the reflexive closure. (19) holds because multi-step can also be zero-step. Yes, thank you. Very, very yes. So, yeah, you can think of it as 0 to n applications of the single-step semantics. 0 to many. Very good. So, is this the same as big step semantics? That's an interesting question. No, it is not the same thing as big step semantics. There's actually an addendum to the part 3, I believe. Yeah, part 3 of Project 1 gives you all of the equations for big step semantics. We're not primarily going to be that concerned about big step semantics in this course, but essentially, I can bring it up quickly. Since it's being asked about. Boop. 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 Big steps. There we go. Big step semantics. So, the difference with big step semantics is, you're not, like, it's a little bit like, you can skip over defining the single-step semantics by saying, this will eventually evaluate to X. And that's what big step means. It means you jump right to the end. So, like, if T1 will eventually evaluate to true, then you get, B if true, big step if true. Same thing with false. If T1 eventually evaluates to 0, then the predecessor of T1 evaluates eventually to 0. It doesn't make as much intuitive sense, like just looking at it. It doesn't make as much intuitive sense as small step semantics. But if you write a function that implements the big step semantics, if you begin creating a function using those rules the same way that you used the small step semantics to create a different the SSOS function in the project, then you'll find that it actually makes more sense once you implement it. But yeah, it's like You step immediately to the result, and you don't worry about, like, the in-between steps. But yeah. Big step and small step do not rely on each other. They do not interact with each other. So, theorem. Uniqueness of normal form. Oh, it looks like I'm missing a... Ooh. Okay. Well, that happens, I guess. I hate it when I mess up a formula. Right over here. There we go. Right arrow, U prime. There we go. Sorry about that, folks. Reloading. There we go. Yes, thank you, Mark. So, theorem. Uniqueness of normal forms. Consider T, U, and U prime to be elements of the set of terms, where U and U prime are normal forms. T eventually evaluating to U and T eventually evaluating to U prime should imply that U is equal to U prime. That is to say, basically this is the same thing as determinacy, but over multi-step evaluation. That is to say, if U and U prime are both the results of multi-step evaluation of T and are in normal form, they must be the same thing. This is a fancy way of saying that a term may not eventually evaluate to more than one normal form, and that is a fancy way of saying that fully evaluated terms must have only one solution. Proof! This is a short one. From the determinacy of single-step evaluation, we already know that T evaluating to T prime and T evaluating to T double prime implies T prime is equal to T double prime. This reduces what we need to prove from terms can't have multiple solutions to terms can't have multiple normal forms in a given chain of single-step evaluations. Here, we use the definition of the normal form. A term T is in normal form if there are no evaluation rules which apply to it. There can't be multiple normal forms along our evaluation path because something in normal form can't be evaluated further. QED. So, imagine a chain of evaluations, right? You're following this chain of evaluations all the way through the language, right? Because of determinacy, we know each step in this chain of evaluations has only one resultant. Like, you can only link a term to another term once, right? That's determinacy. That's why it's a chain and not a tree, right? So, since we know it's a chain, the thing that we need to determine is that there's no normal form in the middle of it that T could also evaluate to, because that's the other possibility, right? The other way this could be satisfied is if some term in the middle of the chain was also a normal form. Then that one would be different from the eventual one, but they would be both normal forms, and like arrow star would eventually lead to either of them. But, of course, the solution to that is, of course, the definition of what a normal form is. A normal form is something that cannot be evaluated further. So a normal form must terminate a chain. And because it must terminate a chain, there's nothing that can happen after it. And because there's nothing that can happen after it, each chain must have only one normal form, and that's the last one. So there you go. Boop. Next, theorem of the termination of evaluation. So, for all T elements of the set of terms, there exists a T prime in the set of normal forms such that T eventually evaluates to it, where N is the set of normal forms of T. Note that this is script N, not natural numbers N. Different N's. Different N's for different ends. Ha! That's a terrible pun that probably nobody heard. I'll say it again. Different ends for different ends. Ha ha. To prove this, let's make some observations about single-step evaluations. Previously, we had defined the size of a term analogously to the size of a tree. So let's introduce a lemma. Lemma! If S evaluates to S prime, then the size of S must be less than the size of S prime. Proving this lemma shouldn't be difficult because S is being evaluated. We know that it's not a normal form. Sorry, that was a period, not a comma. Proving this lemma shouldn't be difficult. Because S is being evaluated, we know it's not a normal form, meaning it must be an if expression. Thank you. According to the definition of size, the size of if then else is the size of S plus the size of each of the components summed together plus 1. Using structural induction, we will assume that our lemma applies to the subterms of S. We know that S will evaluate to either S2 or S3, or that S1 will be evaluated to some S1 prime. Neither the size of S2 nor the size of S3 can be greater than the sum of all three of them plus 1, because that's not how addition works. Our induction hypothesis states that the size of S1 is greater than the size of S1 prime, so we can say definitively that the size of S must be less than the size of S prime. Okay, fine, sure. But wait, did I get that wrong? Did I get that the wrong way around? Yeah, I did get that the wrong way around. My goodness, I'm batting 1,000 today, aren't I? I must have been tired when I was doing this. Sorry about that, folks. There we go. We can conclude that the size of S prime must be less than the size of S. Yes. There we go. Sorry about that. So, we have therefore demonstrated that the evaluation represents a decreasing chain with respect to size. You think you hate math? Yeah. Yeah. You don't have to like math to get a job doing math. You just have to be able to do math. So, remember what we were talking about in the preliminary chapter when we were talking about being able to map things to the natural numbers. Given that size, like you can't have negative size, the size of terms definitely also maps to the natural numbers. So the natural numbers are a well-founded set, so we're going to use that property here. We have therefore demonstrated that evaluation represents a decreasing chain with respect to size. Now we need an argument for whether this chain is finite or infinite. This can easily be determined by deciding if the domain of the size is well-founded. There are no sizes possible which are less than 1. We could make an argument that we could have a size of 0 for the empty set, because the empty set is an element of T, right? Though we haven't defined it this way. We could, though. The domain of size is therefore n, the natural numbers, which is well-founded. Therefore, evaluation chains can't be infinite. They must, therefore, terminate. They can't go on forever because they map to the natural numbers, and the natural numbers don't go on forever. Yeah. Math is a tool for programming for me. Yes. Math is weird now. Where did all the numbers and formulas go? I've got a Calvin and Hobbes comic strip coming up in topic 5 that expresses your sentiment. So, there you go. Stop using random characters from Unicode. No, I have to. So, that's it. That's termination. So, uniqueness. So, normal forms are unique under UAE. They terminate, and that's important. Those are important properties. because otherwise it's not implementable as a computer program, right? Otherwise, like, without these properties, the reason that we're focusing on these properties so heavily is that these properties must exist, they must be established, they must be in place for us to be able to implement this stuff as a computer language. To build a compiler, we have to have these properties. Otherwise, we're just doing math for math's sake, right? Application. If you don't have this stuff, there's no application. So anyway, any questions about that? If not, we will move on to topic 5. Lambda calculus. Like, my oh my. If you guys thought that was... If you thought topic 4 was bad, then topic 5 is really going to bake your noodles. Bake your collective noodle, perhaps. All right, looks like we don't have any questions, so let's move right along, shall we? Untyped lambda calculus. We're going to introduce it. We're going to go over the basics. There are some typographic details that we need to talk about. Then we'll do operational semantics, and then we'll talk about church booleans and church numerals. Think lambda. Think lambda. Think lambda. Think lambda. So, computation, my friends, computation. In the 1960s, where all of this stuff went down, Peter Landin observed that complex programming languages can be understood by capturing their essential mechanisms as a small core calculus. The core language used by Landin was lambda calculus. This is lambda. This is the Greek letter lambda. You will hear it way more than you want to during this and future lectures. So, yep. Developed in the 1920s by Alonzo Church, the lambda calculus was. Lambda calculus reduces all computation to function, definition, and application. The strength of lambda calculus comes from its simplicity and its capacity for formal reasoning. So, all right, I'll tell you why I think you should think lambda. So, in order to get lambda calculus, you need to think in lambda calculus. Fortunately, lambda calculus is reasonably simple. Like, there aren't a lot of rules, and, there aren't a lot of rules to lambda calculus, but you need to be able to pop your brain out, put it in lambda calculus, and have it run in lambda calculus. So you need to think in lambdas. It is lambda time. Is Peter Landin related to Mr. Lambda, who invented lambda calculus? I don't think so. Possibly, in terms of, grad student professor lineage, possibly. If you're wondering who Alonzo Church is, he's the guy who supervised Alan Turing's PhD thesis. So, yep. So Turing. This is the guy who taught Turing. So, languages which are based on lambda calculus. Most notable ones. There are actually a whole bunch, but the notable ones are Haskell, OCaml, actually the entire ML family, and Lisp. Lisp is actually a family of languages, but you'll notice that the character lambda features prominently in the logos for both Haskell and Lisp. So that should give you some indication of how important lambda calculus is. Yes. Inclusion of lambda expressions in multi-paradigm languages has become a trend recently, and here's an XKCD cartoon about that. So, I'm gonna level with you guys. I'm trying to break the record for least 3IO3 appropriate presentation ever with this one, and the fact that XKCD is now at the approved comic along with Dilbert kind of makes me want to pull them all out of my presentations now. So that is why it's called the Church-Turing thesis. The Church-Turing thesis is that Turing machines and lambda calculus are equivalent. And yes, it's because they worked together. Yeah. Professor Farmer, oh, cool. Professor Farmer's in that lineage? That's cool. Yeah, you get geniuses who don't need to attend the university, and then you have the geniuses who do, and they're better. So, here are the tactile as opposed to visual basics. So this is how lambda calculus. We're gonna build up, and yeah, yes, we're going to build up we're going to build up an argument for lambda calculus. So, give me a moment because it has to warm up a little bit. Abstraction is the programmer's most reliable weapon. Lambda calculus is based entirely in abstraction. For a true programmer, the following statement should be instinctively irritating. You should be repulsed by this. Your humble professor couldn't even type that out without using copy-paste. Our instinct tells us to write this as follows. A recursively defined factorial function, and then the factorial of 5 plus the factorial of 7 plus the factorial of 3. Baby's first lambda. So, let's examine the function part of that. Right now, the left-hand side is doing way too much work. That is to say, any work at all. Let's introduce a new operator, lambda, which does the work of the parenthesis n here, above. So, you pull this over here, and you say lambda n dot. That has the same function as saying factorial of n. Okay, so this operator makes this guy into a function that accepts one argument and replaces whatever it receives as an argument everywhere an n appears in there. That's what lambda calculus is. But we're going to go through it thoroughly. In Haskell, this would be written as factorial lambda n. So in Haskell, backslash is lambda because there's no lambda button on the keyboard. Otherwise, they would have used that. It's the button on the keyboard that most looks like lambda. In equation 1, function application is in the traditional form f of x, whereas Haskell and lambda calculus use the space character for function application. So notice here, we're like using parenthesis notation, right? In order to apply the argument to factorial. In lambda calculus, space is function application. You may have noticed that in Haskell, space is function application. So, lambda calculus. In lambda calculus, every goddamn thing is either a function definition or a function application. Everything. There are no states, there are no literals, it's all functions. It's turtles all the way down. The arguments accepted by functions are functions. The results returned by functions are also functions. Everything is functions. Lambda calculus be like, burger. It's burger time. Lambdas. So, here is your syntax. And this is actually the entirety of lambda calculus. It's like UAE, we had like, what, like 10 terms, 7 terms, something like that. In lambda calculus, you get 3, only 3 terms. You have number 1, x, which is a variable name. So any letter can be a variable in lambda calculus. Number 2, you have lambda abstraction. So you abstract a variable over some term t, and then you have function application, which again is the space character. It's some term space some other term. Thank you, Joe. I worked hard on that meme. I even used the be-like terminology, which is normal with memes. How do you like this meme? Onions have layers. Syntax has layers. So, will Dr. Farmer prove that P does not equal NP? Probably not. You find with, like, mathematical geniuses that normally they're done with all of their important contributions to the field by the age of 30, 35, maybe. Yes, okay, thank you. The earlier meme was good, was gooder. Okay. So, layers of syntax. When working with programming languages, it's useful to be able to reorganize and even transform our syntax before applying semantics to it. How are we doing for time? Okay. So, it is very, very common to distinguish your concrete syntax from your abstract syntax. Concrete syntax is the syntax that you, the programmer, actually write. Abstract syntax is a tree structure which contains the terms of the program. We're going to do some abstract syntax trees for some simple lambda expressions. It is sometimes useful to specify even more layers than these. Just on a parenthetical note, the syntax of complex languages can often be vastly simplified via purely syntactic transformations. So, redundant constructs can be simplified to reduce the number of distinct terms. This is also known as desugaring. For example, changing array access to pointer arithmetic in C. Like, C allows you to access arrays by index. But we all know, because we're all smart, that under the hood, all it's doing is it's doing some pointer arithmetic. This means that it doesn't have to verify that 2 different distinct functions work. It doesn't have to verify array access and pointer arithmetic. It only has to verify pointer arithmetic in order for array access to also be, for that to also work. Python does this all over the place. All over the place. Generally speaking, the higher the language level is, the more sugar there is, the more desugaring needs to happen before it gets translated into object code. So, abstract syntax is an excellent way of visualizing a program structure, especially in resolving operator precedence. For example, under BEDMAS, y'all remember BEDMAS, right? The expression 1 plus 2 times 3 would be the left diagram, not the right diagram. So this is how you would break this. If 1 plus 2 times 3 is the concrete syntax, the abstract syntax would be plus operation, 1, and then 2 times 3. So this comes implicit with an evaluation strategy that you evaluate the leaves before you, you evaluate the low-down stuff before you evaluate the top stuff. You have to, you can only perform operations on you can only perform the operations for nodes that do not have a sub-operation as a leaf node. But, yeah. Basically, 2 and 3 are bound, right? BEDMAS trees are evaluated leaf first, but as we'll see in lambda expressions, we may evaluate them using a number of different strategies. What does E stand for? Exponents. In BEDMAS, it's brackets, exponents, decimal. Brackets, exponents, division, multiplication, addition, subtraction. Division and multiplication and addition and subtraction are at the same level, so you can do them in either order. So let's do the abstract syntax tree of a lambda expression. In order to reduce the number of redundant parentheses in our concrete syntax for lambda calculus, function application will be left associative. That is to say, STU is interpreted as apply T to S and take the result and apply U to that. Right? Or, in concrete syntax, S gets T and then U gets, whatever the result is. Scope of the lambda operator. The abstraction operator, lambda, is taken to extend as far to the right as possible. For the following expression, for example, lambda x, lambda y, x, y, x, we would construct an abstract syntax tree as follows. Lambda x, lambda y, then it's x, y, x. So it's x gets y, like y is applied to x first, x, y applied to x, and then x gets applied to that. So there you go. Cool. So there are 3 or 4 of the questions on assignment 4 ask you to produce abstract syntax trees for some lambda expressions. So, let me check the time. We're doing fine. Free versus bound variables. In predicate calculus, we recognize a distinction between free and bound variables. So, in the above, we have there exists an x such that x does not equal y, right? In this expression, x is bound by the existential quantifier, right? Y is not bound by the quantifier and is therefore free. Let me finish the slide, then I'll go back. In lambda calculus, I forgot to put the math thing around that. Oops. Oh well. In lambda calculus, we apply the same concept and the same terms to the relationship between variables and the abstraction operator lambda. So, lambda x, 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 y, and then apply x to that, with this expression, the first occurrence of x is bound. So this x is bound by this guy. But the second one, this guy, this is a free occurrence of x. And this is going to become important later because the substitution operation that happens when you apply the lambda operator, when you apply an argument to the lambda, when you perform the beta reduction, which is what that's called, when you take a function application and a function abstraction, bring them together, you get a substitution operation, and it only substitutes free instances of the variable under consideration. So, we're going to see how that works. So the question is the bottom x the first y, or the first x in x, y, x? Yes! Yes, it is. So it's x, so y is applied to x first. Y is applied to x first. Then x is applied to the result of that. X is applied to the result of that. Boop. Where did that y come from? I just added it. In lambda calculus, there will be free variables that have not been bound to anything, just kind of floating around. You have to understand that and be able to deal with it. Good. Are there any questions so far? I'd like to open up the floor to questions. And in the meantime, I'll show this comic. This is the Calvin and Hobbes comic that I said that one of you would like. So, If x is free, does it mean that it can be substituted by anything? What does being free mean exactly? So, good question. I'm going to pull up Notepad, a Notepad-like application. So, I'm going to use / for lambda. So let's say we had a general expression x, y, z. So in this, all three of these guys are unbound. So when you perform lambda extraction, then the x becomes bound, right? What happens is that if you apply something to this, like u, the result of that will be uxy. So the x is substituted for what's applied, right? But the trick is, let's have a slightly more complicated scenario. Let's say that this guy was x, z. That we had a sub-lambda expression, and that x, the variable x, was also used here, right? So what happens when you try to evaluate this is you go here. It kind of occurs in a couple of steps. You say, okay, I'm taking this expression, and I am substituting x becomes u, right? So from the top level, this x is now considered free, but this one is still bound. So when you perform the substitution, you perform it there, but not on the inner lambda. This x is not free, it's bound, so it doesn't get substituted. And that's why free versus substitution, it makes a difference. Listen, Moonstar, don't hassle me, okay? Don't hassle the Hoff. Yeah, I know, right? I mean, to be fair, this is like a 5th grade... Calvin in the Calvin and Hobbes comic strip is supposed to be like a 3rd grader. So this is a 3rd grader's understanding of philosophy. But yeah. So the comic is, I don't think math is a science. I think it's a religion. A religion. Yeah, all these equations are like miracles. You take two numbers and then you add them, and when you add them, they magically become a new number. No one can say how it happens. You either believe it or you don't. The whole book is full of things you have to be accepted on faith. It's a religion. And in the public schools, no less, call a lawyer. As a math atheist, I should be excused from this. Actually, it was the original SpongeBob movie reference. So, can I explain on the slides, I presume, why the second x is free? Was it because it was outside of the brackets? Yes, it was because it was outside of the brackets. That is precisely the reason. So, when we say that this lambda operator applies as far to the left as possible, that means it's contained within, like, this parenthesis, this set of parentheses. So the effect of the lambda doesn't travel outside of this thing, which kind of contains it. So yeah, that's why this is free, but this one isn't, because this one is inside of the parenthesis with the lambda operator, and this one is not. Math will be ended by computer science. We will end it. Yes. So it's now 1:21. For any of you who are, if you have any further questions, please please, let me know. Could I update the topic 4 slides on Avenue? Yes, I could do that. That's a perfectly reasonable thing to ask. Old math has not yet ended, and new math is created with the abuse of Unicode characters. Yes. Wouldn't it be better to just use different variable names to avoid this free-bound confusion which might arise? The problem is you're gonna run out. Like, we're gonna not to you know, jump too far ahead of where we are currently, but like, we're gonna be doing some actual math with this stuff, and yeah, it's not gonna work if we have to choose a different variable name each time. So yeah, we're gonna do some actual math with this stuff. Oy. Can I give you an exact date and time of the midterm? Good gravy, I haven't even thought about the midterm yet. So, I'll give you, yeah, so, the week of October 31st. Let's see. What is October? What is that week? So, okay, so normally I put them on the Saturday, and I make them a take-home test. So I don't see any reason not to do that this time. So the exact start time will be 9 a.m. on the 6th of November. The end time will be 9 a.m. on the 7th of November. You will have 24 hours to complete the test, and it'll be an open book test, so you can use the lecture slides, if you like, for reference. So yeah, that'll be it. I know, it's like Moonstar, it's the worst thing in the world having to continuously update the course outline. It's like, come on, can't they, like, it would be so much simpler if they just lined up weeks with, like, okay, so this is what we need to do. We need to, like, okay, so the number of days in the year is 365. We need to find some number that's divisible by that divides 365 evenly, and then make that the length of a week, and that way we don't have to change the dates ever again. Right? That would be awesome. That would be fantastic. Expected writing time will be 2 hours. You aren't going to burn us at the stake. Yeah, 2 hours probably, yeah. 2 hours assuming you've paid attention. So I am saying to use the lunar calendar. Does the lunar calendar, like... No, I don't think the lunar calendar, because you still want to maintain, like, you still want it to be relative to the sun, right? Because otherwise you mess up the crops and stuff. Maybe. But, no, like, I think, like, let's see what number would work. I think a 5-day week, like, 5s would certainly work. You know, 365 divided by 5. Yeah, 73 weeks in the year. We could manage that. That would be fine. Then we'd never have to change a date again. And then, well, Let's see. Is 73 a prime number? Let's see. Prime numbers. $73 is a prime number. Damn it. All right, so 1 month, 73 weeks. Make it a system like weeks go from 1 to 12 and then days from 1 to 7. Yeah. Who cares about crops? Yeah. Let's see. There's got to be 365 divided by 15? Nope. $25? Nope. $35? Nope. Well, I suppose if it's a prime number, then that's useless anyways. It's 5 multiplied by a prime number, so obviously there aren't going to be any other factors. Yeah, okay. Oh, here's an idea. Okay, here we go. This is it, all right? 73 weeks in the year. We take 1 week off in the summer. Everybody just gets 1 week off in the summer, right? Then, it's 6 weeks. Every month has 6 weeks. We get to keep 12 months, right? So we keep 12 months, right? We take 1 week off in the summer that's got no month, like everybody just goes to the beach and has a good time, all right? And then everything's solved. Everything's solved. I just fixed time. You're welcome. Leap years, pfft. That's fine. We'll have every 365 years we'll have a leap year instead of a leap day. Huh? We'll just skip. We'll skip a year. Once every 4 centuries. Anyway, that's it for today. Thank you very much for coming to class. And we'll see you tomorrow. I love ya tomorrow. It's only a day away. I hate it when it does that. What am I even doing? What am I even doing? Anyway, take her easy, folks.